So now Levin, who came from Swinburne and the US Melbourne group, but recently joined into Faculty of IT in Monash. Today he's going to talk about anesthesia, but he also worked on epilepsy as well. Do you want to use the mic or? Yeah.
All right. Yeah, so I'll be talking about anesthesia research we've been doing at Swinburne using the MEG and simultaneous EEG recordings. And this is done with David Liley and Andrew Palentritu, who's up and back. And yeah, so I've got a question mark here about reductions in consciousness because we're studying NMDA antagonist-based anesthesia, and a lot of those drugs at low levels have dissociative effects. So you sort of become detached from your external sensory input. And so when people become unresponsive with these drugs, it's not entirely 100% clear what's going on, whether they're having a reduction in consciousness or being altered in some way that, yeah. So generally, there's lots of different anaesthetics out there, and they all anaesthetize people. And we assume that's an unconscious state, and it seems to be. Whether it's the same unconscious state, it's not clear. So it could be pushing the brain in different directions, but maybe there's some universal change that can be found that would, help point to some brain network or region that is involved in generating states of local levels of consciousness. So that's the main sort of motivation in this work. And then, so we've been doing EEG and MEG imaging with both xenon and nitrous oxide, and they're both NMDA antagonists. Then the typical anesthetics that are used are propofol and sevoflurane, isoflurane. They all act by enhancing inhibition instead. So we're sort of going against the grain and looking at these NMDA antagonists that are less studied, and also MEG is not hasn't been studied very much in terms of anesthesia. So we look at three different things. So we look at basic power changes at the source level. So we do inverse source reconstruction. And then we also look at source level functional connectivity and then neurophysiological variable estimation. So I'll go through all of those as we move along. So, a lot of people in the literature, so for example, Melanie Bolly has a review from 2017 that talks about posterior regions of the brain being involved in generation of sort of global or levels of consciousness. And in 2010, Hudas has a book, Anthony Hudas, who's an anesthesiologist, has a book that focuses more on anesthesia, and because parietal cortex is involved in sensory integration, he proposed that parietal areas and breakdowns in connectivity in these areas would be linked to anesthetic reductions in consciousness. So that's sort of captured here. So that comes to our study. So I should have EEG here as well, but so some of the stuff I'll talk about is EEG and MEG, and some is just MEG. So we have 22 healthy males. We have two conditions, so each male experienced xenon and nitrous on different recording days. And basically, xenon is a general anaesthetic, so it's used in Europe for surgery, whereas nitrous oxide is typically used in dentistry, and basically high levels of nitrous oxide that would lead to loss of consciousness lead to other side effects like hypoxia and emesis, nausea and things like that. So we only brought people to loss of responsiveness with xenon, whereas with nitrous and xenon, we delivered concentrations that have, you can think of them as having an equivalent behavioural effect. So there's this thing called MAC awake, which is the concentration at which 50% of people don't respond to speech commands. And so the loss of responsiveness concentration for xenon is 1.3 macawake. So you expect most people not to respond to speech commands. And then for the other levels, for the first 3 levels, they basically correspond to 0.25, 0.5, and 0.75 macawake. So they're all sedative levels. And then we track people's responsiveness using an auditory task, which is just listening to 2 tones and then pressing a button for the button that corresponds to a specific tone. And essentially we compare conditions. So we have baseline conditions. So we have awake eyes closed is our main baseline. And so we compare that 50 seconds in that baseline to 50 seconds in the other recordings. But I'm not sure if that's on every single thing that I'm going to talk about today. It's for the work that I've been doing, but I don't know for Andrea's stuff. So we have this Job article that people can check out to see how we do this, if you're interested. So it's simultaneous EEG and MEG, and so the first thing I'm going to talk about is power changes at the source level. So I don't know how well you can see this diagram here. Have you got a laser pointer, or I'll just use? There we go. Yeah, so this just shows the nitrous delivery. So this, the dark red here shows that basically nitrous is increased to the first level, and then decreased to white, which means there's no drug, or just oxygen essentially, and then it's increased to the next level, decreased and then increased, and then the same for xenon. And so here we're basically seeing recording for the accuracy of the auditory responsiveness task, and then over here the gas concentration for the loss of responsiveness level for xenon. So as the red curve goes up, xenon concentration increases, then we get a period of loss of responsiveness here. So, so basically we have the MEG and EEG data, and I'll show you a picture of the setup in a second.
So wait, so is there no period where the accuracy is either 0 or 100%?
Well, these are basically showing every time someone doesn't respond at all, so it's not a smooth curve, it's just...
So it's not really like percentage, it's really like responding
yes or
or
no.
not.
Yeah. I'll just go back because I didn't really explain the setup. So here you can see a subject in the MEG scanner, so they've got an EEG cap on, and they're getting the anaesthesia delivered by a mask, and the anaesthesia machine's outside of the room, and so the gas is passed through the waveguide into the room to the patient, the subject, sorry. And then, so we have the different gas levels, and so we do source reconstruction in the different frequency bands, which is sort of pointed out here. And so here you just see some of the raw data. Here we see the points, so these blue points here correspond to where we're doing source reconstruction to on the brain. And then we look at power in the different frequency bands, and we also look at gamma in the low and high. And I won't get into the details of the frequencies. And then, and so then we try to look for changes in power, looking at the group level across the brain. So we're looking for either increases or decreases in power.
Can I ask a question about this?
Yeah.
Just a general methods question. Do you use both the MEG and the EEG to do your source reconstruction, or do you only rely on the MEG?
We do both, but it's separate. So because we didn't have a clock synchronization, electronic clock synchronization, the data aren't perfectly synchronized. So we haven't done beamforming using both data at the same time. It's just beamforming separately. So multiplex MEG and co-register it in order to do the source imaging. So this basically summarises the most significant changes that we see. And so these are all sort of new results that we're just going through now as Andrea's writing up her thesis. So it's all kind of new to me. So typical to a lot of anaesthetics is that you get an increase in low frequency power, similar to sleep. And so we see that here for the loss of consciousness state. So these diagrams are basically the group level changes between the baseline and level 4 of xenon, the highest level of xenon, the level that gives loss of responsiveness. And so we're basically seeing frontal changes in low frequencies, and similar here. And whereas we don't see many changes with, I guess, alpha per se. I can't see this axis so well here. Yeah. So, sorry, I can't read those figures at the moment. So blue is probably the baseline, and red is the loss of responsiveness level. So you can see that here, the higher frequencies. So this is averaged over the whole brain, I would say. So, and then if you look at nitrous oxide at the highest levels considered, then we're seeing a decrease in alpha in the MEG, and so that's consistent with what's known with studies of nitrous oxide with EEG, but we do get some weird effects with the EEG. So here you're not really seeing much strong alpha change here, but you're seeing in the EEG you see a decrease at this lower concentration rather than this higher concentration.
Wait, so is this data coming from exactly the same subject done on recorded at the same time with just different modality?
Yeah, and then this is group level.
Yeah, but is it normal to see this level of the discrepancy between the MEG and the EEG at the source level?
Well, they pick up different sources, orientations. So one's meant to pick up tangential, one's meant to pick up radial.
Yeah, but after that, it's kind of blurred, right? In terms of source.
Yeah,
quite a bit.
But yeah, I mean.
But now we know when we do MEG and we're looking at localization of epileptic sources and stuff like that, that EEG and MEG can actually have quite different responses. So often we do the EEG-MEG source localization. We'll sometimes find that the MEG will actually localize the source much better than the EEG, and sometimes the EEG much better than the MEG, and we both use LCMV kind of being approaches for both of them. So as Levin was saying, it very much depends upon the orientation of the sources, which is sensible.
I mean, that's kind of worries me about sort of believing in the result of the source localization and either way.
Well, I mean, there is a small possibility that we've made an error, but I think it's very unlikely that we have, because we've collected considerable amounts of data. These are group level comparisons. The LCMV algorithm is the same for both. Basically, it runs.
You can see some similarities, like if you look here, you can see that here in the EEG and MEG. But then, say this patch here, you don't see the same patch here.
So if they are picking up different sources, and would it be fair that actually both are correct? That in fact the brain is active in the
Yeah, I think that is
junction
right.
of
I mean,
the
the
two.
complementary measures, just as if we did bold, we'd get something different as well.
I think it would also depend on the source reconstruction method, and we've just focused on LCMV, so yeah, it's an open question still. So so we do see agreement largely between the MEG and EEG here for the lower frequencies, but less for in the alpha band, and then we do see an increase also in the gamma band in the MEG. So, and the MEG sampling rate is much higher, so that's why we can probably see it in the MEG, but not the EEG. that's one thing. And then the next thing we looked at, or Andrew's been looking at, is functional connectivity. So it's basically the same steps up until this point here. And then she basically looks at functional connectivity in the different frequency bands as well as the broadband signal. So basically 1 to 50 hertz, or is it higher than that?
149.
Yeah. And then we look at imaginary coherence and then power envelope correlation. So essentially 2 different ways of trying to look at functional connectivity. And again, we basically compare the different gas levels to baseline and look for significant edges in the network, essentially. So, and then we look at the global level in terms of global efficiency, which essentially, when you think about it all, it's just basically the average functional connectivity in the network. So, so just showing some basic results. So here we have the significant decreases when you look at xenon minus the baseline. And so this is the loss of responsiveness level here. And so it's increasing here. And so the aqua colors are basically all of the connections that were significant except for the frontal, frontoparietal and parietal ones. So frontal is purple, frontoparietal is blue, and parietal is green. And yeah, it's kind of hard to pick it out here because I'm just seeing this. I saw these figures for the first time today. So one thing is I'm still not sure about. So is the normalization the same in each of these figures?
Yeah.
So across these are the same. So the widths here.
You mean the weight itself?
Yeah, the weight.
Maybe if you're not familiar, then she should actually present it.
No.
Okay.
So
By then I will be unfamiliar with this.
if there's questions, Andrew can come back up and answer them.
Okay.
Yeah. So so then I think the next diagram is probably a bit more useful because I'm a bit confused about something going on in here, but I won't describe it. So if we look at frequency-specific whole brain global efficiency, then basically when we look at xenon relative to baseline, we see both a decrease in imaginary coherency and a decrease in the power envelope correlation. So we're seeing a breakdown in functional connectivity, essentially. And with nitrous, we don't see that. So here, I don't have the legend, so the different colours are the different frequency bands. And so we're seeing a decrease in all the frequency bands, and it's pretty robust. Whereas over here, it's much less clear. And then here, we're seeing frequency-specific changes when you compare the specific equimac awake levels for nitrous and xenon. But I won't go into that much, and we can come back and ask questions later. That's just there accidentally. So the next step is basically talking about neurophysiological inference. So trying to image neurophysiological variables across the brain from this data set. So basically we have we do the beamforming to estimate the source time series at every grid point on the cortical surface, and then essentially we assume that the source time series is linearly proportional to the mean membrane potential of the pyramidal cells of a neural mass model. So this neural mass model contains pyramidal population, spine stellate cell, inhibitory population. And so we assume that for each source, there's one of these neural mass models, and it's not connected to any other region. We just assume that it's driven by some noisy input U, which could be a linear combination of external inputs from different parts of the brain or neighbouring columns, but because the inference problem is so difficult, when you try and connect all the basically the cortical points together, it's easier or simpler and more efficient as a starting point to basically just try and infer these variables within this network, within this neural mass, for basically when they're not connected up. So for each population, the inputs are processed by a postsynaptic potential kernel, and then they sum and to give you a mean memory potential for a given population, and then the output is basically the membrane potential passed through a sigmoidal rate function. And so what we want to do is estimate the mean membrane potentials of each population within the model, and then also the connection strengths between the populations. So these alphas, which you can think of as population level synaptic strengths. And so we want to do that for each current source that we estimate. And this is just for the MEG data. So as before, I told you about how we do the MEG source imaging, and we have basically 4,700 points on the cortical in cortex that we try and estimate neurophysiological variables for. And we basically use a filtering technique that we developed. We applied it first in epilepsy, and we use that to estimate our variables, and in particular, and then we do group level statistics across all the subjects that I've talked about, and basically compare the baseline to the different gas levels. And this is just to give you an example of what we do. So, and it's basically the most where the most significant changes happen. So here we see a 42% xenon, which is the condition that gives loss of responsiveness relative to baseline. And so we're imaging the changes that are significant at the group level. So we don't see much in terms of pyramidal cell changes. Most of the changes are for inhibitory cell membrane potential here. And then pyramidal to excitatory connection strength, you don't see much. In terms of what you might expect with xenon anesthesia, because it's an NMDA antagonist, you would expect it to basically reduce the excitatory strength. And we can see that it reduces excitatory strength for this connection. So this pyramidal to inhibitory connection is an excitatory synapse, whereas for this connection here, it's an excitatory synapse, but here we see it increase. So one of the issues here is whether or not the model is accurate enough to describe the data accurately. But so we view we think that because the estimation problem is so complicated, you need to start with simple models and then do more work to figure out what needs to be done to better describe the data. And so potentially you can think of these estimates here as hypotheses that could be tested in experiments, potentially in animals, or if you could ever do it in humans some other way. But basically we're trying to develop a method that helps us to image this stuff in humans, so it's probably more practical to figure out experiments to validate this in animals. And so, yeah, so this is sort of work in progress. So I thought I'd leave this as a question mark rather than telling you anything useful. Go ahead.
Okay.
I was just interested in what are the behavioural manifestations of people when you give these doses of probably toxic things.
Yeah.
What happens to them? I mean, can they function very well, or what do you see?
Well, at the way we did the study, in a way it was kind of risky, because you get these behavioural things that happen at the sedative level. So if you put them straight under, you wouldn't get. And so sometimes, some subjects were removed because they had like vasovagal effects. So I think I can't remember the exact details of that, but then other things are like at certain levels you might get relaxation of the esophagus and things like that, and the breathing pathway, and so sometimes people might look like they're about to vomit and things like that. So for some subjects we had to exclude them because they were having, they were moving too much and things like that. And then in terms of the perceptual experience, it's, I think it's not entirely clear whether people totally will remember the unresponsiveness period and just before that, but they do have a lot of descriptive reports in the time period before they become unresponsive. And Andrew knows all about that.
Well, they're highly hallucinogenic and psychotomimetic, so subjects move a lot and they report like vivid hallucinations, dreams, at least at the sedative doses. To me, it resembled sort of the hallucinogenic literature like you would find for LSD or specifically ketamine, I suppose, because they're very similar in pharmacology. But I guess that's all I can say is that. I don't know what happens when they lose consciousness. They don't say they remember anything, but I don't know what happens when I sleep most of the time.
So nobody has probably done this kind of serial awakening paradigm during this transition to loss of consciousness using this type of drug, right? Probably.
No.
Too difficult. Too difficult. Because we were at Swindon, which is an alternative environment, so we had to be extremely careful about how we administered these gases. So we got 2 anaesthesiologists from St. Vincent's Hospital to actually supervise all inhalations and stuff like this.
Right.
And more particularly, we had to buy a low flow closed loop delivery system, which took a while to deliver and was an extremely complicated beast to use. So no one would normally not do that. Normally, what they do sometimes for epilepsy in childhood is that they will actually sedate the child before doing an MEG, but typically it's just with an intravenous dose of propofol or something like that. Whereas what we did was we were administering stepwise gas concentrations. And the reason we used the gas instead of like an intravenous agent is that we were sure what the effect site concentrations were when we were actually doing the relevant measurements, which you can't do, of course, if you're using an intravenous agent, because you have to get blood samples and then you have to fluff around and stuff like that. So the advantage of using a gas is you have the entire gas concentration measurement that you can use to ensure that the gas levels equilibrate before you then actually do the recording.
Yeah, but that's totally fine and all. And my specific question was a serial awakening paradigm, which is basically done by this, sleep experiment or mind-wandering experiment, basically. Especially at the low dosage of the xenon. If you do that and then you just randomly ask, are you awake or are you, hallucinating and things like that. Randomly probe the subjects. And then possibly sometimes, people wake up, sometimes randomly reporting some, dreams.
That's true, but we couldn't do that, so we had to just use continuous auditory performance task, which was assuming that their level of consciousness is maintained. What we got them to do afterwards was to actually fill out the altered states of consciousness form, and also to give us a subjective report, so
Yeah.
all that information.
But in principle, is it never possible to just ask the experience during the low dosage?
Well, because we were only focusing on resting EEG and stuff like this, we didn't want to ensure that it was...
But in principle, it can be done, right?
Oh, in principle,
I think so.
absolutely, yeah. In principle,
Also, like when we read the ethics, the literature for that sort of stuff was only becoming popular really in the state. So the ethics was already done with.
Yeah.
But there's no reason why you couldn't use some anaesthetic xenon and get them to do something much more sophisticated, cognitive behavioural. No.
I think it has been done. So
It's a bit difficult for them to talk when they've got the mask on, of course. So, and so that does make things difficult, and particularly with the xenon, you want the seal to be really, really good.
Right.
Because xenon is a very expensive gas,
I
so,
see.
you know, and Swindon is a very poor university, so, you know. Yeah, so basically the only thing we could get to do was really button presses. The other thing was also because of socialization, we wanted to make sure their eyes were closed all the time, so obviously visual stimuli weren't easily administered and stuff like that. So really we were just restricted to button presses, auditory stimuli, and subsequent subjective accounts.
I see. Okay. Is there any other questions, comments?
Yeah, I think that it's something Yuval Nir, who is now in Israel, told me that he has been working on data, so intracranial data, so epileptic patient being implanted with intracranial electrodes, and working with a surgeon. They managed to, during the implementation, do it a slow version of the implantation, and having gradual level of anesthetics while putting the electrodes little by little in the brain to record brain activity with different level of anesthetics and at different depth. So in terms of testing the model, you want to test with this balance of excitation, inhibition, that kind of data, if at some point it's released and it's made publicly available, which I doubt, could be fantastic, because it's kind of the missing link with what you have so far.
Yeah, part of the issue with data like that is you still dependent on algorithms that try and figure out if the spikes are excitatory cells or inhibitory cells, and stuff like that. So there's still work to be done.
And then maybe, shall we go to the coffee break? Yeah. Then we'll come back.